introduction. Thanks for the organizer. Thanks also ECNWF, the host institution, for organizing this workshop. I'm going to present something operational. It's no, I hope you can go because you was spending a lot of calibration and so on, then to show you the use of this information, some of this kind of information. Then first, what we are going to do now is to move to the drought and drought in agriculture areas. That is what we are interested in FAO. The main user of this system is inside the house, inside FAO. That is the Global Information and Early Warning System. That is a team of experts in economics that they have to monitor in the food situation around the globe. Then there are no experts in remote sensing, there are no experts in agrometeorology, and they use this as another index combined with the indicator as prices of socioeconomic information. What will be to monitoring drought at global level? We can use information from the Met stations. The problem is that normally we have gaps in certain areas, Africa or other areas. We have different time series of information and different quality of this information from the network. The other possibility is to use rainfall estimate that we was already analyzed during this meeting, but we find that every rainfall estimate have an error of estimation, and it depends. You have to know if you are applying this rainfall estimate, what is the error in the country that you are using. Whereas applying some kind of information like this, like ECNWF data era interim, when I was working with the Joint Research Center, we find that there are underestimation of the Sahel, Somalia, and other parts. And if you don't know your error, when you're using some kind of simple models like water balance to see if there are going to be some problem of drought affecting the crops, you are going to find that areas that you never can start the simulation because the precipitation estimate is very low. Then the other possibility is to use information of vegetation index. In this case, what the other option after trying the first option of a rainfall estimate, that we said that we can use NVDA as a proxy of information, that it will be possible. They have another limitation that everybody knows also when we use remote sensing. There are noise, there are different fields, but in this case, it's no estimation. If you, what do you record is what do you see on the ground. Then there will be maybe some advantage to use this, and that was the idea to implement this kind of system based on vegetation index. A short slide only to the basic theory behind this is that we are going to work with two bands, the red one and near infrared. And normally what we are expecting is when the plant starts to cover the ground, we are the reflection of the red will be decreased because it's using in the photosynthesis. In the moment they are going to be more is developed, more will be less the amount captured by the satellite. This is the general principle. If you have a water stress, then in this moment you are going to have the stomach will be closed to try to don't lose the water, and in this moment the CO2 will be decreased and the rate of photosynthesis will be decreased, and then in this moment the reflection of the red band will be increased and captured by the satellite. This is the principle of this. I don't go too much detail. This is also, you can see also the same, what I say, the same basis. Red is going to be decreased and near infrared increase, and depends of the coverture of the plant of the soil. We are going to use indices here, not directly the NVDA. It's some indices that was introduced by Kogan in the United States, and this is the Vegetation Health Index. The Vegetation Health Index have two components. One is the Vegetation Condition Index and the Temporal Condition Index. They're going to standardize this. I'm going to show how this is the standardization quickly. He took the, going to take the NVDA, current NVDA, and going to take the minimum, so the difference of the minimum, and going to divide by the maximum minus the minimum. What I say is that in a time series of 30 years, imagine, you are going to have the minimum here in green and the maximum. Then we are going to separate two components, that is the maximum that the ecosystem can give with when the weather conditions are not good, and the maximum expression when the weather conditions are in good conditions, then in the maximum. Then the standardization will be from 0 to 100. So near 0 is near to the minimum, and near to 100 near to the maximum. Then this will be the idea. Then we are going to do the same with the channel 4, that is the temperature. That will be an inverse correlation of the two indexes, because we are going to have better expression of the vegetation, and the temperature will be decreased in this case. If the vegetation have suffered from some stress, the temperature is going to increase. And the combination of the two we are going to use is that we are going to get the vegetation health index, and we are assuming at global level that these two values have the same value. So the A and the difference will be. This is not true, because depending of the crop, depending of the situation, we can get different values of this calibration, but at global level we are going to make this hypothesis. Okay, up to here what was already known, that was proposed by Kogan. What is new? We are going to do a step forward, because our objective is to mimic what normally the remote sensing expert is doing and analyze this information, to provide a system that will be run automatically in near real time every 10 days, at global level, 1 kilometer resolution, and they're going to analyze the information only where are the crops on the field. What it's going to do is we are going to detect the start of the season and end of the season of each pixel at 1 kilometer, and we are going to analyze only to this temporal window the analysis in real time. This will be the first temporal aggregation that we are going to do, and each time they arrive a new decade of information, they will be average with the previous one. That means that instead to follow the classical approach that we are using, creating anomalies and try to detect what is happening in the anomaly, you don't need to see what is happening first, because it will be integrated in the last decade that you are going to analyze. The second integration that we are going to do is each pixel will be classified as a drought pixel or no drought pixel. In this case, we are going to classify when the value of vegetation health index is below 35. That was proposed by Kogan in different areas that he tested, and is related with the crop yield. As soon as we have this, we have inside the crop mask, we are going to have all analysis will be done at administrative level, but inside the administrative level, we are concentrated in the crop mask, in the areas that we know approximately where are the crops. And inside the crop mask, we are going to classify how many pixels are classified as a drought, and then we are going to have the percentage of area affected by drought in this crop, in this agriculture, in this administrative area. In other ways, it's like this. You are going to have vegetation health index values. We are going to have the value for each pixel, and then we are going to classify the pixels in drought and not drought pixels. And then we are going to put a crop mask, where are the crops and where are not crops, and quantify inside the crop mask where are the percentage of pixels not affected by drought. It's a simple approach. Then is this. We are going to use this global crop mask that was produced by the Joint Research Center, and this is a global product that is a blend of different land use studies that was available at that time. Of course, when you zoom, you can have the resolution and the quality will be depend of the availability in the country that you are going to zoom. But for global studies is what we have available, and this could be changed if we have an improvement in the global crop mass. We have the start of the season and end of the season. For the first crop season, we are going to analyze 2 crop seasons at global level, and then we are going to estimate the first and end based in the spot vegetation data at 1 kilometer. This is the situation that looks global level. At the start, here is the time, and then each species is going to have this one time of start and end for the integration. The final results at the beginning we was expressed in there are a product that is the boundaries of the different countries that they call goal. Goal 0 is the whole country. Goal 1 is the province level of whatever in the different countries, and goal 2 will be like a district. At the beginning, we press the results goal level 1, but after we discovered it, we noticed that if we go really a goal level 1, goal level 2, the results are better and looks like it was a pixel. But remember that we are expressing the results for the whole administrative unit, goal level 2 in this case. And we see this one here. If you average, you have a better situation of the drought on this county. That is, this part was more affected than the rest. And we decide to go for goal level 2. Let me show you some information on the web. That is what we have. The official launch of the web, I hope, will be next month. But you can also already visit the web on internet. That will be, if you go to agricultural stress index, you are going to find the information at global level of the current information. This moment at the second decade of October of this year, and then you can see what is the situation. There are some areas that start with, here is the percentage of area affected by drought. The situation around the globe looks near good. It starts some areas that start to present some delay of drought, some delay of the crop season that could be drought in this area. To have a good interpretation of this index, you need to look this one that gives you how is the progress of the crop season, because around the globe there are going to be some plants that is going to start, so that will be planting, but others in the middle, others will be harvest. Then you know to see if the warning is, you have to take attention of this warning, is you look this, how is the progress. If you are at the start of the season, maybe the red areas is only meaning that it will be a delay of the planting. But if you are in red areas in the other map, and you are near to the end, that means that you are going to, what is expecting is a reduction of the crop yield in these areas. Okay. You have other indicators. This is the vegetation health index. This is a pixel level, 1 kilometer resolution, that also is temporally integrated. If the people want to see a pixel level, what is the situation? Okay, this is real time, but if you want to see historical information, you have 30 years of information here, and you can select every 10 days that you want in the past to see what was the situation, I don't know, of this was third decade of August, in 2000, we can see what is the hottest spot. But remember that that everything is integrated temporally. That means that it's not the situation exactly in this decade. That is different the anomalies that you can see. You have to see that the anomaly represents only this specific decade. This one represents the decade, but from the start of the crop season. That is a temporal integration. If you want to see summaries around the globe, what happened in the past. For example, if you want to look at the 84 that was the drought in the Sahel, you can see here that the final result for this crop season, that is 84, that you can see the Sahel and the other areas that was affected, even Southern Africa, Botswana, Zimbabwe. You want to see other, like 2003 in Europe, you can see like this, and this is the final result. You see Europe and another part of the world that was affected at the end of 2003. Then we can look the hottest spot around the globe, and you can detect the spring drought, because the way that is defined in this case for the global is the spring event. I don't see moderate droughts in this moment for this system. I see the spring event that happened in the past. If you want to see a specific country, I see people from Turkey. Let me to find Turkey. You can see 2004. There was some problems in May on these areas. Yeah, you have some problems here. Turkey, you can see the annual summary of the past, and you can see the worst years, 2007. But 89 seems to be a very bad year in Turkey, and this is one of the La Nina years that was produced a lot of drought around the globe, even the La Nina in El Nino in this case. You can see also this graph, and this case, as you can see, NTVA by any goal level 1 in this case for Turkey, and compare with the historical data, the previous year and the current year. If you want to go to, sorry, this is precipitation. You want to see, in this case, ECNWF data, decadal, and you can compare with the average. You see the maximum, and you can see the previous year for all the administrative levels of Turkey. You can see accumulated rainfall on this. You can have the maps of the anomalies. You can also, if you are interested to see NTVA, like it's the anomaly, the classic approach, you can see all vegetation condition index of the vegetation health index. Other thing that is possible to do is to download the information. If you want to download the extreme events for each of Turkey, you only go here, and they're going to export to Excel for the whole percentage of area affected by for the whole country, or for administrative areas. You are going to have the percentage of area affected for these administrative areas, and you want to do some kind of correlation or use the data for crop year forecasting or any of the different studies that if you want to do. The goal level 2 is possible to receive, but only as a request, because it's too many information to put everything on the web at this level. But it's also possible to do. From here, what I can. Okay, let me. I think for this is okay. What we have is the benefits up to now to this is we are reconstruct one database of a 1 kilometer resolution of 30 years. For do that, we simulate the method that started in 2007 with the NOAA data, that is the same sensor from the 80s, and then we create a time series of 1 kilometer resolution, simulate first in NOAA, and then continue in METOP. Let me tell you something about what is the next? We have the global. The global, the idea is to support youth people, that they can zoom and look if verify if the hotspot is correct or not around the globe. But now we are developing a standalone tool based on that to support regions and countries. This will be delivered to the country, and we can do things that from the global is difficult because the amount of data. We are already 10 terabytes in information on the database. Then what the idea is to put this information in FTP, of FAO FTP, and the standalone will be possible to cut the latitude, longitude of the area of interest, download the archive, and receive every 10 days the information through FTP, and then do the analysis more in deep in the country or region. What is the idea? In some assumptions that we take it on the global, we can improve. For example, A and B, that is the same value to the two indicator. We can take some statistics from crop yield, from rice, for maize or sorghum, and you can look what is the real value what is the real weight when you analyze these indices in relation with this specific crop. In the global, we have 10 crops together that we put as a global crop mask. In the standalone, the country can select the crop mask for maize, the crop mask for rice, because it will be different conditions. Then you can do the analysis. You can also change the levels of, you want to do the analysis instant to administrative level, you can do by agroecological zones. It will be the possibility to change this information from us in administrative areas analysis. Other thing that will be introduced in the standalone is a weighting average of BSI. In the BSI at the beginning that I showed you, I did a simple average. But what happened that I start to look in the past, I find that there are some areas that crops was affected, but at the end of the cycle. At the end of the cycle is very important because it's the flowering and grain filling. Then, normally, when you are modelize this in the crop models, you give in the water balance more weight to these phenological phases. That's why the idea was to introduce exactly the same sensitive of what do you get with the crop coefficients from lysimeters and apply to the profiles. Then we can multiply the profiles by these crop coefficients, and any time that you have a problem captured by satellite, you are multiplied by the sensitive of the plant of water stress, and you give a weighting of depending of the phenological phase. Here we are testing how they change the profile of, for example, this one that was the third. In the good ones, they go down. That means that they are sensitivity when you introduce the profiles. Let me see what else we are trying to do. We are in the standalone, we are going to do the weighting, but we are going to introduce different classes of drought. Not only the extreme drought. We can introduce exceptional drought, extreme drought, severe drought, moderate drought. This way, we are no limitation for the number of maps that we have to produce automatically, and we can try to ponderate a map with the stream, but also produce maps with different classes of drought. Okay. Other thing that we are going to introduce is I don't go in detail, I only transfer the concept. We have 30 years of information from the past. And then we are receiving each 10 days a new information. Then we can calculate the probability that this pixel in the middle of the crop season can be classified as a drought pixel at the end, based on the information from the past and the current information. And you can calculate the omissions and the different statistics to see what is your error. And this will be something that we tested, like for example in the Sahel, that you are at the beginning, you estimate what will be the areas that have more probability that at the end will be affected by drought. You are in the middle of the crop season, these areas become, and when you are already close to the crop season, then you have already the areas that have a more probability to be affected by drought. Other application that can be done is use this as a remote sensing indexing crop assurance. The data is delivered at administrative level. Now, normally the crop assurance, they would like to have this independent data. That there are advantages when you implement this in remote sensing because the resolution. Normally when the index was at the beginning introduced in crop assurance using the rain gauges information, the stations, but you introduce error when you do interpolation, whatever method that you are using. There are uncertainty that you are introducing. If this uncertainty will be increase the premium of the contract. Then in this case, you are going to have an independent source of information based in remote sensing, and you can aggregate administrative level to sign a contract. For example, in this case will be the 30 years of information from the province Eastern in Kenya, and you can sign a contract when you have 70% of area affected in Eastern province. And of course, you will cover 3 events. If you want to cover more events, you have to pay more. In NIASA, this trigger you cannot use. You have to go down because NIASA is more humid province, and then you can try to sign a contract when you are 40% of area affected in province, and you will cover 2 events stream the past. Okay, I try to finalize quickly. I almost done. And also that I tried to do recently is that I have 30 years of information at goal level, also at district level. I can correlate with some indices of El Nino to see where are the more sensitive. We know more or less what are the areas global, but we would like to see the impact in agriculture. Where are the areas more sensitive? And then here, I didn't finalize the study, but we have a correlation, the Spearman correlation, where are the most sensitive areas at this level for El Nino. And you can see in red that is the positive correlation. That means that when the index, the sodium oxidation index increase, the area, agriculture area affected by drought will be increased. And then we discover what is this, what are the more sensitive administrative in the different countries. For example, here you see there are some different sensitivity to drought, to the El Nino in India. The same for the second crop season is possible to do, and also the frequency of drought if you put the 2 crop seasons together. Maybe the last thing that I would like to show you is also that can use this as a forecast the production. For example, in Syria, this year, this is when we extract the agricultural stress index, but it's possible if you have some data of crop yield from the past to do a model based on the agricultural stress index and the production, in this case is for wheat and barley, and you estimate the crop yield, and based on the information from the country of the area, you can know your error of estimation of the crop yield, and you can use an area given by the government, or make a scenario of the last average of the 5 years, and you make estimation of the production. And this will be give you an indication in this specific country that they have problem to see really go and measure the information from the field. Of course, they have to be adjusted because of the situation. I think I stop here, and thank you for your attention and waiting up to the late.
Question? Yes. Do you have anything to implement this vegetation acting with the other parameters and the infrared visible on satellite interface?
I was
something like H-SAF. I mean, sorry, more.
Okay, the idea question at first if I have to implement another, okay, using other parameters. There will be, I was thinking on that because it depends on the availability of information. For example, Copernicus, it was also interesting that if I put other kind of indices like FFR, maybe instant to be, there are convergences of indicator. There will be a way to really confirm that where the drought hotspots are detected, using another kind of vegetation index or soil moisture, in this case, will be converged to the same. Will be a possibility, but we have to find a project to fund in this kind of thing. They have to be global also to compare in this way and have access, free access to the data. But yes, it will be a good idea to check.
On the global map, you have loads of no-date areas. Is this something you're going to add later, or is that something that's like North Africa, for example, all gray, but no data? I don't know. It seems too much.
These gray areas. These gray areas is because are no crop there. Are desert areas or are forest areas that are masked out. You see, all is this desert. Only the grow have here because it's the agriculture area. Normally it's there. Normally the areas arrive to the agriculture arrive to the southern part of Mauritania, and then they are masking with the GRC 2000, the forest areas also. Then the idea is to concentrate in the agriculture areas only. Agriculture, yeah, there are 10 crops that are put together to produce the mask. I masked out forest, I masked out pastoralists, but we are also implementing this in pastoral areas that are different than the crops. Or you can monitor in forest if you want. But the idea is to separate the different vegetation because at different time of analysis. Pasture is almost continuous of forest, and crops are limited to a specific time. And for example, Somalia have 2 crop seasons. In Central America, you have 4 crop seasons. Then you have to limit to be more clear for the user. Okay. You was expecting more information, more crops. Okay.
Okay. We hand over to the first part of the session. Let me thank again all the we'll start at 9 tomorrow and we will stay by 4 p.m. Okay.
But just very quick part. Very good concept of school. We've got 4 cars.